Dr. R. Hemavati is an assistant professor in mathematics in Queen Mary's, Chennai. She has specialized on functional analysis. Having 12 years of experience in teaching, she has won various awards for her performance. She has published papers in 14 international journals, 3 national journals, and has presented papers in 10 international and in 5 national conferences. She is also one of the editors for an international journal.
Welcome to UGC lecture series. Earlier sessions we have dealt with probability density functions, probability mass functions, distribution function, moment generating function and characteristic function. When the characteristic function is given, you can find out the PDF using inversion theorem, and also you can find out the characteristic function when the PDF is given using the original definition of characteristic function. So, such kind of problem is dealt with in this session, and also we are going to deal with the new concept called cumulant generating function and cumulants. It is in continuation with the moment generating functions, characteristic functions we have already studied in the previous sessions. So, going ahead with the continuation of the previous sessions, let us do one problem in finding the characteristic function of a random variable when its PDF is given. The question is, find the characteristic function of the exponential distribution f of x is equal to 1 by lambda e power minus x by lambda when x is greater than 0. Any random variable has this type of PDF, then it is called exponential distributions. This kind of standard distributions like binomial, Poisson, normal, exponential, all these type of specific discrete and continuous distributions, you will be dealing it later, and we are going to find out the mean and variance of x using characteristic function. Also we have found out mean and variance in various methods using exponential, using expectation and using the original probability density function or probability mass function, and using moment generating function, and this particular problem is finding the mean and variance using characteristic function. So, first of all let us find out the characteristic function. Okay. So, what is given? Given f of x is equal to 1 by lambda e power minus x by lambda for x is greater than 0 and lambda is greater than 0 is given. Let us find out the characteristic function. Okay. According to the definition, pi x of t is equal to expectation of e power I t x. Okay. And according to the definition of expectation, it is integral minus infinity to infinity e power I t x into f of x dx. But what is f of x? F of x is defined only for x greater than 0. So, we have to alter the limits as integral 0 to infinity e power I t x, f of x is 1 by lambda e power minus x by lambda dx. How to write this in the format so that we are going to integrate 1 by lambda integral 0 to infinity, it is e power I t x into e power I t by lambda. What is the previous one? E power I t x into e power minus x by lambda. So, let us combine e power I t x minus x by lambda into dx. Okay. So, 1 by infinity, I shall write this in the format so that it is suitable for integration as e power minus 1 by lambda minus I t into x dx. So, now I am going to integrate 1 by lambda e power minus 1 by lambda minus I t. So, it is e power minus 1 by lambda minus I t into x divided by minus of 1 by lambda minus I t. I will tell you why this is written in this format as minus is taken outside, because only when e power minus infinity it becomes 0. So, that we have to make this particular quantity 1 by lambda minus I t as a positive quantity, so that negative into positive into infinity then only gives you e power minus infinity. Okay. So, this is written as 1 by lambda by, I will simplify this part as minus is taken outside, and it becomes 1 minus I t lambda by lambda. and the remaining part is substitution, e power minus infinity minus e power 0. This particular lambda gets cancelled and you have only e power minus infinity minus e power 0, which is equal to minus 1 by 1 minus I t lambda into 0 minus 1, which is equal to 1 by 1 minus I t lambda. We have found out the pi x of t, the characteristic function of exponential distribution, as 1 by 1 minus I t into lambda. Okay. This is particularly valid when this particular quantity, as I already told you, is positive. That is 1 by lambda minus I t should be greater than 0. That is you must be having 1 by lambda is greater than I t. This particular quantity 1 by lambda should be greater than I t. Okay. Next we have to find out the mean using characteristic function. Okay. Mean mu 1 dash is equal to 1 by I d by dt of the characteristic function, then you have to put t is equal to 0. This is the formula. So, 1 by I of d by dt of pi x of t is what is pi x of t? 1 by 1 minus I t lambda, 1 by 1 minus I t into lambda. We shall differentiate this, it is 1 by I, differentiation of 1 by 1 minus I t lambda is minus 1 by 1 minus I t lambda whole square into differentiation of this with respect to t, that is minus I lambda. Okay. So, I gets cancelled and minus into minus it becomes positive, and then you at the most you have to substitute t is equal to 0. Okay. So, what is that equal to? When you substitute, you will have lambda by 1 minus 0 square, right. So, this is equal to lambda, right. So, mean is equal to lambda. Next we have to find out variance. Variance is equal to mu 2 and mu 2 is equal to mu 2 dash minus mu 1 dash square. This mu 1 dash just now we have found out, that is mean, that is equal to lambda, right. Next we have to find out mu 2 dash, where mu 2 dash is equal to 1 by I square d square by dt square of characteristic function at t is equal to 0. So, this is minus of one time differentiation we have already done, so that I will use it, that is I lambda, we will go to the previous one and see what is that, I lambda by 1 minus I t lambda whole square. So, I lambda by 1 minus I t lambda whole square, this at t is equal to 0. We have to differentiate it one more time, I will take it outside, minus I lambda, and one more time differentiation is minus 2 by 1 minus I t lambda whole cube into minus I lambda. This ultimately you have to put t is equal to 0. Okay. So, this minus into minus into minus it becomes minus, and I into I square, and lambda into lambda is lambda square. This is minus 2 I square lambda square by 1 minus I t lambda whole cube. This you have to put at t is equal to 0. I square is minus 1 and it becomes 2 lambda square by 1 minus 0 whole cube, which is equal to 2 lambda square. So, mu 2 dash is equal to 2 lambda square. So, what happens to the variance now? The variance is equal to mu 2, and mu 2 is mu 2 dash minus mu 1 dash square. So, 2 lambda square minus mu 1 dash is we have found out as lambda, mu 1 dash square right. This is actually mu 2 dash minus mu 1 dash square, right. So, 2 lambda square minus lambda square, which is equal to lambda square. This is your variance. Okay. Hence, summarizing the results, what all we have found out? We have found out pi x of t is equal to 1 by 1 minus I t lambda, and we have found out the mean is equal to lambda, and we have found out the variance is equal to lambda square. Before going to the next problem, let us have a break. Welcome after the break. Before the break, we were doing a problem of finding the characteristic function when the PDF of a random variable is given. Using the original formula of characteristic function we have done, and this particular example is vice versa. Given the characteristic function of a random variable, we have to find out the density function of x, that is probability density function of x, and this can be done only using the inversion formula for characteristic function. Okay. So, we shall do this now, and what is given? We are given pi x of t is equal to 1 minus modulus of t for mod t less than or equal to 1 is equal to 0 for mod t greater than 1. Okay. And we have to find out the PDF. To find the PDF f of x, using inversion formula, do you remember the inversion formula which was taught in the previous session? Inversion formula says that f dash of x, capital F dash of x, differentiation of distribution function is equal to f of x is equal to 1 by 2 pi integral minus infinity to infinity e power minus I t x into pi x of t dt. But pi x of t is defined only for modulus of t less than or equal to 1. Okay. So, what happens? 1 by 2 pi, and we have to change the limits because pi of t is existing only for minus 1 to plus 1 of t, right, e power minus I t x into 1 minus modulus of t dt, right. And this particular modulus of t has two definitions, right. Any mod function is minus t if t is negative and is equal to t if t is positive. This is the modulus function definition. So, accordingly we have to split the integral as minus 1 to 0, which is negative, plus 0 to 1. 1 by 2 pi integral minus 1 to 0 e power minus I t x into 1 minus of minus t, right, into dt plus integral 0 to 1 e power minus I t x into 1 minus t dt. Okay. Now we have to integrate this, which is equal to 1 by 2 pi. Okay. What is the integration? Minus 1 to 0, we have to integrate 1 plus t into e power minus I t x plus 0 to 1 1 minus t into e power minus I t x dt. We will do the integration 1 by 2 pi. First is 1 plus t into e power minus I t x. Since the integration is with respect to t, x is considered as constant, minus I x minus 1 into e power minus I t x by minus I x whole square within the limits t is equal to minus 1 to t is equal to 0. This is first integration, plus the second integration is 1 minus t into e power minus I t x by minus I x minus differentiation of this is minus 1 into e power minus I t x by minus I x the whole square, and the limits are for t is equal to 0 to t is equal to 1. We have to substitute t is equal to 1, and at the same time we have to substitute t is equal to 0, t is minus 1, t is equal to 1 and t is equal to 0. let me close this big bracket which I opened here. Okay. We have to carefully substitute the limits. So, 1 by 2 pi, I will substitute the limits. First I substitute 0, 0 if I substitute 1 by minus ix minus 1 by minus ix whole square, this is for 0, right, minus, next we will substitute t is equal to minus 1, t is equal to minus 1 gives you 0, 0 minus, here when you substitute t is equal to minus 1 e power ix by minus ix whole square plus, seeing this we have to substitute, so please adjust, and this is 0 and t is equal to 1 plus e power ix by minus ix whole square. Okay. Then minus lower limit e power minus e power 0 by minus ix minus into minus plus 1 by ix whole square. Doing this is very carefully you have to do. What is that simplification goes as? It is 1 by 2 pi 1 by minus ix, 1 by minus ix is it repeated anywhere? 1 by minus ix is here 1 by minus ix, here 1 by plus ix. So, shall we cancel this? Okay. After cancelling, this is minus 1 by ix whole square and this is minus 1 by ix whole square and this is 2 times, right, and this is 2 times, all x square terms are 2 times. So, 2 by minus ix whole square plus 1 time when you substitute t is equal to minus 1, it is e power ix, and t is equal to 1 if you substitute e power minus ix here. Okay. So, it is e power ix plus e power minus ix by minus ix whole square. Okay. So, what happens? 2, this is minus 2, right. Okay. And what do you have? This is 1 by 2 pi 1 by 2 pi 2 divided by I square x square, it is minus 2 times, right, minus 2 plus this is 2 cos x by I square x square. Okay. So, 2 is taken outside commonly and then it is cancelled and you have I square is minus 1, 1 by pi, you have 1 minus cos x by x square. This is f of x. Okay. Hence, we have found out the probability density function as 1 minus cos x by pi into x square for the given characteristic function. So far we have dealt with the characteristic functions, characteristic function properties and a problem finding characteristic function for probability mass function, finding characteristic function for probability density function and finding the probability density function when the characteristic function is given. So, the next concept is cumulant generating function. Okay. It is in continuation with the functions we have already seen. We have already seen moment generating function and this is in continuation with the moment generating function. We have the definition as cumulant generating function. Let x be a random variable, then the cumulant generating function k x of t is called the cumulant generating function of x, which is defined as k x of t is equal to log to the base e of mx of t. It is logarithm of moment generating function, okay, provided the right hand side is convergent series, provided the right hand side, because logarithmic is an infinite series, it has to be convergent. So, the cumulant generating function will exist only when the logarithmic expansion is valid as a convergent series in powers of t. Okay. From the basic definition, the cumulant generating function means it generates cumulants. We have k x of t is equal to, since it generates cumulants, start with the k 1 of t, 1 is not written because logarithmic series starts always with x. So, k 1 of t plus k 2 into t square by 2 factorial plus etcetera plus k r t power r by r factorial plus etcetera. Okay. And this is actually logarithmic of mx of t. What is mx of t? It is moment generating function. From the basic definition, it is it generates moments, right. So, this already we have discussed. So, it is written in terms of moments is 1 plus mu 1 dash plus mu 2 dash mu 1 dash t mu 2 dash into t square by 2 factorial plus etcetera plus mu r dash into t power r by r factorial plus etcetera up to infinity. Writing this infinite series, you can find out the cumulant generating function. Okay. So, what is the relation between cumulants and the cumulant generating function? Okay. So, we can write the Kr is rth cumulant, which is a coefficient of t power r by r factorial in the cumulant generating function kx of t. So, what is its relationship with the moments? Relation between cumulants and moments, using the logarithmic series and the corresponding cumulants, we have the relation between cumulants and moments as a mean. Mean in terms of moments is mu 1 dash, mu 1 dash is equal to k 1. Similarly, variance is equal to mu 2 and which is equal to mu 2 dash minus mu 1 dash square, this is equal to k 2. And then we have the third central moment mu 3, mu 3 is equal to k 3, mu 3 we know that it is mu 3 is equal to mu 3 dash minus 3 mu 2 dash mu 1 dash plus 2 mu 1 dash cube. Okay. So, mu 3 is equal to k 3, this is what is basically we are interested in now. Mu 4 is equal to k 4 plus 3 k 2 square. Based on this discussion in this session, you can do an exercise that finding the characteristic function of the random variable whose PDF is given by f of x is equal to 1 by b minus a for a less than x less than b. This is uniform distribution. Also, you can find out the mean and variance of the characteristic function. Based on the cumulants, you can have the question as discussed briefly about cumulants. So, in this session, we have dealt with some examples in finding the characteristic function of continuous random variable when the PDF is given and vice versa, that is when the characteristic function is given, finding the PDF. Also, we have dealt with the definition of a cumulant generating function and the relationship of cumulants with respect to cumulant generating function and moments. Thank you.